So our next speaker is Ezgi Toraman. She's an assistant professor of energy engineering and chemical engineering, at Pennsylvania State University. She's also very active in the wider academic community for both of those fields. Her research is in the field of chemical reaction engineering and catalysis, with a focus on developing new processes, new materials, and technologies for efficient and sustainable use of non-traditional feedstocks, things like shale gas, biogas, biomass, and plastic waste. Prior to joining Penn State, Toraman did her postdoctoral work in chemistry and energy at the University of Delaware. She also has a BS and an MS degree in chemical engineering from Middle East Technical University in Turkey, and a PhD in chemical engineering from Ghent University in Belgium. So thank you for being here.
So first of all, thank you very much. It's really a great honor to be here today. So when I received the news, I just couldn't believe my eyes. So thank you very much for this opportunity. So I guess that I can use these. So today what I would like to do, in fact, first of all, to share my story, because it was really, when I was asked to prepare this presentation, I also had this opportunity to reflect back and see how I came to where I am now. And I realized that it was quite a journey. So I'm from Turkey, and recently the official name changed to Turkey. So it seems that we all need to use that. I remind myself all the time now. So I am from Ankara. I was born there. I grew up there. So I always lived with my family. So to be honest, going abroad was quite a challenge for me. So, but I took that step. So I was very fortunate that I did my studies in Middle East Technical University, so where I got introduced to also research, and my first research experience was in polymer chemistry and biotechnology. So, and I started working with biomass. Afterwards, I moved to Belgium to join Ghent University for my PhD studies, and it was really an amazing experience for me because I learned a lot then in the field of reaction engineering, and I continued working with quite non-traditional feedstocks from biomass, like genetically modified biomass samples, to algae and plastic waste. And my PhD advisors, Kevin Van Heem and Guy Marin, they were of course very instrumental for my career, but I also want to mention this great chemist who was a great mentor for me, Hans-Heinrich Carstensen. So, but when I was thinking about my PhD, in fact, I mean, of course, I published papers, I got introduced to, let's say, analytical chemistry, like GC times GC, which I use a lot now for my research. But beyond that, in fact, I realized that there are two key takeaways from my PhD journey. So first of all, I could experience firsthand how fundamental science propels technology innovation. Why? Because here you will see a setup that I designed each part of it. I basically put it together, made it work as the first person studying solid to gas transformation in the whole department for biomass research. But also here you will see a pilot plant steam cracker. So I was able to, with my eyes, could see that we were really starting from the micro scale and we were going to the pilot scale. And that's really very important because later you will see how it shaped my research and how I see research. But another thing was that when I say that, okay, I always lived in Ankara, I was always with my family, but my curiosity for new knowledge really said that, okay, you need to go out of your comfort zone. And I stepped out of my comfort zone, I moved abroad, and it was not easy. So I learned how to navigate challenges for my personal life, for at work, but all these, in fact, experiences helped each other. And I would say that also the support mechanism that I had via my friends, collaborators, and mentors were really very important. So this was another, in fact, key takeaway from my PhD journey. And then I said, okay, so now let's even go further from my home country. And I was I received an offer to join University of Delaware Energy Institute and Chemical and Biomolecular Engineering to join as a postdoctoral researcher, and there I started working in shale gas conversion. And Dion Vlahos was my postdoc advisor, and I would like to mention that, in fact, the experience that I had in his group really encouraged me to also pursue my career in academia, and it was really very, very helpful. And I would also say that it's very important, all these places that we are in, all these people that we are meeting, in fact, they become our lifelong friends and collaborators. For example, we just came together in Quebec, Canada, as part of our annual International Reaction Engineering meeting, and all those people, in fact, one of them is here in the audience today. We are all in academia, and we would love to continue working together, and we are friends for lifetime, I think, and it's very important. So. And one of the things that we, in fact, did during my postdoc was opened up many opportunities for my research career now. So there was a science paper, and there was a new chemistry, in fact, discovered as part of the science paper. So methane is a very stable molecule. So in order to activate this molecule, of course, even if we use a catalyst, we typically need to go to very high temperatures. And when you go to those high temperatures, the chemistry can become very complex. So you have catalyst, you have also gas phase chemistry. So it's not easy really to explain that chemistry. So there was this amazing science paper that they showed that they can convert, for example, methane to aromatics, olefins, and hydrogen with very high carbon atom utilization efficiency, very high one-time pass methane conversion, and no coke formation. So this was really fascinating. And what we wanted to do, we also wanted to explain what is the chemistry behind. And for that, we developed a macrokinetic model which contains more than 500 species, 9,000 reactions, really elementary steps. And we were able to, in fact, explain the chemistry behind that new chemistry, these mechanisms. And this, in fact, opened up many new opportunities for process intensification. And then now, for example, in my group, we are looking at new catalyst formulations, and also we are also looking at ways how we can electrify this process, make it also more energy efficient. So this brings me to this part, my research group. So I am one of the researchers who started her career or his career during the times of pandemic. So I started in 2019. After 6 months, pandemic hit. And my group is, we do experiments, modeling, but we are at the core of our research is experiments. And I didn't have access to my lab space for almost 2 years, because in the state of Pennsylvania, construction stopped as well, so no renovation, nothing. So it was quite stressful, but we survived and we even flourished. So I'm very happy to see now my group members, how diverse we are, and I'm really very fortunate with my group members, because they are the ones enabling the research that now we are doing together. So that's very important. So in my group now, there are 2 chemistries that we are looking. So as Craig mentioned, I am working in the field of reaction engineering and catalysis. So one of the research areas that we are working very hard is related to plastic upcycling, design for recyclability, and also we are specialized with one analytical technique, GC times GC. Later, I would like to explain a bit this technique, because that technique is very, in my opinion, very important when it comes to developing chemical processes for complex feedstocks such as biomass and plastic. And another thing that we are working on, in fact, is developing a data management and analysis hub. And in fact, tomorrow I'm going to give a talk about it as part of the Big Data in Polymer Chemistry Symposium. So this is something that we are also very passionate. And the other one that I already mentioned is about how we can convert like biogas, biomethane to useful chemicals. So I think I don't need to talk about it to this audience much, but we know that the plastic waste management we are not managing it so well, and because of that, in fact, less than 10% of the plastic waste is recycled. But there are many reasons about it. Plastic waste, even if you just think of single polymer, there are many things in that single polymer. You can have additives, and all those things, in fact, making it very complicated if you want to somehow put them back into this circular economy. if we want. And for example, there are some feedstocks such as multi-layer packaging films, carpets. They are very hard to recycle. And even when you think about like, it's a waste. There are many things. Even if you want to sort them out, it's very intensive, but there will be always something there. And that's why, in fact, when we want to develop technologies, we need to also take into account all these factors. So this is one of the projects that I am leading, and I want to show that because if we are dealing with such a problem such as plastic waste, recycling, upcycling, we need to have an interdisciplinary team. And in this, for example, project, we have chemical engineers, specialized like me, reaction engineering and catalysis. We have experimental computational people. We have TA, LCA people. We have data scientists. So, and we also have collaboration between industry and academia. So this is very important. But what we are trying to do, and this is one of the main focuses in my group, is understanding the interaction effects between those mixed polymers during chemical recycling. And one of the main goals of this project as well is to develop mechanistic understanding of these process components. For example, here we are looking at a two-stage process where we can do non-catalytic and catalytic upgrading later. So, for example, this is one of the examples where we look at a catalytic process, and what we are doing basically, we are looking at the kinetics, then we do kinetic analysis, and we are trying to understand what kind of reactions are happening. So this is another example where we are looking at two different types of polymers, and here we are again looking at these interaction effects, but we also, in fact, what we are doing, we are trying to take advantage of algorithms such as machine learning, and then we can, for example, predict those mesos kinetics, and then it can help us for experimentation. So this is something that I want to show today because this is a setup. Here is the reactor where we are using very small sample sizes. So we are working with sample sizes of like few micrograms. And this is extremely important because when it comes to developing kinetics for example, solid samples, we really need to work with those small samples, and we can eliminate those transport phenomena. And this is very important for us to develop those intrinsic kinetics. So due to the time frame, I will be skipping those parts. But the other thing that I want to show here is the importance of analytical chemistry, which is typically underestimated in chemical engineering. For example, when it comes, if we were using just one DGC, we would not be able to, for example, see all those aromatics that we see here. So with GC times GC, we are able to identify and quantify more products, and then our basically kinetic investigations are more accurate. And with GC times GC, basically what we do is that we put another dimensionality into the separation space. So, but why are we doing all those things? Why are we putting all this effort to focus on the kinetics and to have all this detailed composition? Because in the end, what we want to do, we want to develop experimentally validated kinetic models, and then those kinetic models will be put into process simulators, and we can do process optimization. So basically, fundamental understanding of reactions is really necessary to develop, scale up, and optimize technologies. And that's what we are doing in my group. Of course, this brings me to the last part where I would like to, in fact, acknowledge all this support from my previous institutes, collaborators, my current collaborators, funding agencies, and of course the C&EN team for this great recognition, and all the team and everybody here for attending my talk. Thank you so much.
So I think one of the things you're working on is a big dream in the chemistry world right now is, of course, is to take waste and turn it into the feedstock that you can put right back into the same crackers. But some of your work is talking about how different pyrolysis oil is, especially from plastics, than the crude oil. And even the crude oil isn't all one thing. I wonder if you give us a sense of, from a chemical standpoint, how different are they? How close are we to be able to convert the big crackers down in Louisiana, taking all plastic waste? Is that a pipe dream, or is that a work we can get to?
I don't think that it's a dream, but I don't think that at the moment we have the knowledge for many plastics. So we know, let's say that if we have a pure polyethylene or pure polypropylene, we know what kind of products we would get and how we can, let's say, put it to a steam cracker. We can, because we will know the product composition and many things. But when we are talking about mixed plastics, there are so many components. So we really need to build the knowledge in terms of what kind of polymeric and non-polymeric content that we have and how it is affecting the, let's say, the quality of the oil that we obtain, how we can optimize the process in this space, and then we will be able to also evaluate how we can incorporate it into our steam crackers maybe more intensely. I would say that we are getting there, but we need to put the effort, and that's what we are doing.
So kind of a follow-up question. Pyrolysis oils coming from the different waste plastics, part of the problem is that you have chlorides, halogens, olefins, and I know you show that you can do the aromatics, polyaromatics, monoaromatics. What about the olefins? Do you have a good method to be able to analyze the olefin content in those? Because GC by GC kind of...
So we can, in fact, analyze the olefinic content, and we can also, if we have both olefinic and aromatic content, with the GC times GC, we can separate them. So
Right.
if you have a 1D GC system, so the olefins, the alkanes and the olefins and the aromatics can be overlapping.
Correct.
So we can basically lose that information.
Correct.
But with that's why with these advanced analytics, we are able to characterize them with high accuracy.
Even with, because on the GC by GC, the paraffin and the olefins don't separate very well. So are you using the time-of-flight mass spec to target it?
So what we are, we can separate the paraffins and olefins with the GC times GC. We also use a TOFMS.
Okay.
But what we have now as a problem when we have, for example, isomers. So
Okay.
we are not able to really handle with that. But what we did now in my group, so we upgraded our system with soft ionization. So we are hoping that with let's say, reduced amount of fragmentation in the mass spectra, hopefully we will be able to also resolve this problem of identifying isomers.
Okay. I'm part of DO2P, which is a recycled solvent method, and we're trying to find out, to come up with a guide for pyrolysis oil analysis. Because crude oil, no, you have some patterns, but when you start with the waste plastic, you don't have any patterns, so you start from scratch. So any kind of help, we use SFC also to do some separations. And so DO2P, if you're looking for that, that's...
Okay. Thank you.